Hello, wonderful 3H students. Today, or this week rather, we are going to be talking about rational functions and all of the features of rational functions. So we're going to describe a rational function just like we described functions last week, but this is a function you potentially have never seen before. So we're looking at the features of rational functions, write down today's date, keep yourself organized. All right, so what is a rational function? A rational function can be written as a ratio of two functions. So in other words, it's a fraction. Okay, so basically what happens in our typical rational function, we have some number over a variable x. All right, so if we have the function f of x equals 1 over x, it ends up graphing like this right here. And the reason it graphs like this is because think about this here. So we have the value 1 over x, right? Well, that cardinal rule of math tells me that I am absolutely not allowed to divide by the value of 0. So x cannot equal 0 because that would give me an undefined value, right? We can't take something and turn it into nothing. You cannot divide by 0. So x is not allowed to be 0. So what happens at x equals 0, which is this, hold on, let me see. X equals 0, which is right here, right? So here's our line, x equals 0, that vertical line there. And we get what we call an asymptote. We're going to define this in a moment, but we talked about it last week, right? So an asymptote is an undefined part of the function. So this region where there are no values of x, we cannot have a value of x equaling 0. And then also, if you think about y equaling, so if we have y equals 1 over x, right? And I wanted to resolve that equation for x instead of y, I would multiply by x on both sides, and I'd get xy equals 1, and then I'd divide by y, and I would get x equals 1 over y. Therefore, we have another problem. We can also not have a value of y that is 0. So y is not allowed to be 0 either. So what we get here is another asymptote. So we have both a vertical asymptote, in this case at x equals, okay, hold on. Okay, so we have a vertical asymptote here at x equals 0, and then we have a horizontal asymptote at y equals 0, because both those values make the function undefined. You cannot have x equal to 0 or y equal to 0 because it breaks the function, right? We divide by 0, that is not okay. So rational functions show us what happens if we're allowed to have basically all values except a specific value, in this case 0. We call this the mother function or the parent function. The most basic version of a rational function is 1 over x. All right, so vertical asymptotes are like this, yes? So straight up and down, and they're always going to be x equals. And these asymptotes, we decide what their value will be by determining what value of x would break the function, right? So in our first example, we said 1 over x. X can't be 0 because that breaks the function, right? We're not allowed to divide by 0. All right, so here, x cannot equal 0, right? So we're going to have a vertical asymptote at x equals 0. We get a vertical asymptote because that value is undefined, okay, just like that first example. However, what if we have something like this, where we have 1 over x minus 5? Well, now I need to determine what value of x would make that denominator equal to 0. So basically what I'm saying is, all right, I need to determine what value of x would make this equal to 0. So if I have x minus 5, what value would I plug in for x to make it 0? Well, obviously you can solve this using algebra, or you could say in your brain, well, obviously 5 minus 5 is 0, so x is not allowed to equal 5 because that would break the function, which means at x equals 5, we have a vertical asymptote. So if I were to do a rough sketch of this graph, I would go to x equals positive 5, 1, 2, 3, 4, 5. I would draw my little dotted asymptote line, and then all of these are going to follow this curvy pattern, which we'll talk about in a minute. But it's what we're focusing on right now is identifying where is that asymptote going to be. If you think about this equation, what we have again is, let me change the colors up so we have an idea here. So what we have is y equals, or f of x, right? F of x is just y dressed up in its fancy function clothes. We have y equals 1 over x minus 5. If I wanted to resolve for x, we'd have to, or if I wanted to get rid of this denominator over here, I'd have to multiply by the whole thing, x minus 5. Over here, I'd multiply by x minus 5, and then I would divide by y. So I'd get x minus 5 equals 1 over y. If you need more fraction help, holler at me. So y cannot be 0, right? So even though our vertical asymptote shifted, our horizontal asymptote stayed at y cannot equal 0, right? So our asymptote there, our equation is actually y equals 0 because we would break the function if y actually did equal 0. So it's undefined there. All right. And that's actually going down here, right? That's a horizontal asymptote that I just talked about. So our vertical asymptote's in red, our horizontal asymptotes we're talking about in green. Okay, so what I just said was y equals 1 over x. If we resolve, we get x equals 1 over y. So y cannot equal 0, or y equals 0 is a horizontal asymptote. Okay? All right, what if, though, instead of just having a number over a fraction, we also have this other number plus 2 over here? All right, so now what we have is y equals 1 over x plus 2. So the first thing I need to do is subtract 2, because I can't get rid of this fraction business unless it's the fractions by itself. So I'm going to subtract 2, and I get y minus 2 equals 1 over x. That same process is going to flip those two values, and I'm going to get x equals 1 over y minus 2. Again, if you need to do that whole process out, please do. So we get y minus 2. So now I need to ask myself, all right, what value of y would break this function? What value of y would break this function? So y is not allowed to equal 2 now, because if y equals 2, when I take 2 away from 2, I get 0, and now I have an asymptote because you cannot divide by 0. So this horizontal asymptote would be at y equals 2, would have a horizontal asymptote there. All right, so when we talk about domain and range on a function like this, if you think about this function, really, we're going up and down forever and ever, right? Zoom in here. This goes on forever and ever up. This goes on forever and ever down. So it's going absolutely everywhere except, okay, so it's like absolutely all real numbers with one key exception, where these asymptotes are, right? Because the asymptote breaks the function. It's undefined there. So when you're talking about domain here, we're talking about domain, right? Then we're talking about all the x values. So we're talking about our x values. What can x be if we're talking about domain? I did say domain on this one, right? Okay, good. So x values, what is our domain here? Well, that wouldn't be these arrows. That would be, so let's erase those because that was misleading. That would be range, right? So let's talk about domain. Same thing though, right? We're going all the way to the left, all the way to the right, except that one value where we are undefined, which is where we get our asymptote. Boop, 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 right there, right? Okay, so we get this vertical asymptote at the value that breaks the function, and that is the only value that we're not allowed to have. So when we're talking about domain, we're going to say the domain, domain would be all real numbers, right? Because it's absolutely everything, except the one exception, which would be x is not allowed to equal wherever that asymptote is. In this case, it looks to be on 7. So x cannot equal 7. So basically what we're saying is everything, oh wait, but there's one little teeny exception that we need to note for you. So instead of saying like 2 different from negative infinity to 7, and then from 7 to positive infinity, right? We're just going to say everything except 7. Okay, so same idea for range, but now we're going to look up and down. Same exact idea. We're going up forever. We're going down forever with only one exception. And the one exception, of course, being anywhere that breaks this function. Again, we're looking horizontal now. So where do I find that? It's where these curves approach but don't touch, right? So again, when you're looking for an asymptote from a graph, you're looking for where do these curves get really close to, but clearly they're not actually making it there. All right, so this looks like -3. Woo. Okay, so we have y. Y is not allowed to equal -3 here. So our range is going to be all real numbers except y cannot equal -3 because that's going to break the function and give me an undefined value. All right, so we're going to graph these rational functions and make sure that we draw our asymptotes. All right, so if we were doing this in class together, we would be doing a lot of Desmos today. We'd plug these in, we'd try them out, we'd look at them in Desmos. So that is something I'd like you to do. I would like you to, and we'll do a warm up with this, but I'd like you to graph these in Desmos, just play with what happens as you change certain values. And I'll be more specific what I mean in a second. All right, so we have 1/x. Again, this is the mother function of this, or the most basic version of a rational function. We know that the most basic version of the rational function is going to have an asymptote at x equals 0. It's also going to have an asymptote at y equals 0 because those values break the function. It is undefined there. All right, then if we think about creating just a quick x-y chart here, and we were to think about the values that we would get out of this function, let's just create a quick XY chart so you get what I'm saying. But again, you can check these out in Desmos and see what's happening. So if I plug in 1, then I get 1, right? 1 divided by 1 is just 1. If I plug in 2, then I get 1 divided by 2, which is 1/2. If I plug in -1, again, 0 is not going to work. It's going to break the function, so I'm just going to ignore it for now. If I plug in -1, I get -1. If I plug in -2, I get -1/2. So let's just plot those points real quick. 1, 1, and then 2, 1/2. All right, what if we did something like 1/2? Okay, so think about that. What if we plugged in 1/2? So now what we're saying is 1 divided by 1/2, right? So 1 divided by 1/2, you'd invert and multiply. That's going to give us an output. Oops, that's going to give us an output of 2. So this is going to, at 1/2, we're going to go up to 2. So you can see how this curve is formed. So we're going to get a curvy line that approaches both my horizontal and my vertical asymptote. The same exact thing is going to happen on the negative side. So we go -1, -1, right? And then if we have -2, we go to -1/2. I don't know where my negative sign went there. -1/2. And then again, if I were to plug in -1/2, then we'd get -2 out. So -1/2 would give me -2, which is right there. And again, this is the pattern that they will follow. So you're going to get these two parts of this function. This is a discrete function because of these asymptotes. You could not trace this entire thing without picking up your pencil, right? So it's discrete because of the asymptotes, and it's going to look like that with a few variations. Okay, so again, you're going to do this one yourself. So pause. Don't do this just with me. Give it an attempt on your own. All right, so first thing I would do is figure out what value of x will break the function. X is not allowed to be -1 because -1 plus +1 is 0, breaks the function. So x equals -1 is going to be my asymptote. Right there. So there's my nice little asymptote for x equals 1. Again, because I don't have any of those plus or minus outside of the fraction, as we did in this second example here, I don't have anything that looks like that, right? I just have a fraction. When that's the case, it's going to be the same for y as it is for x, in which, or not, it's just going to be y will always not be allowed to be 0. So y can't be 0 because of that fraction thing we talked about. So you get a asymptote there as well. Pretend that's a dotted line. Okay, then again, this is going to follow a set of patterns. You could create a table to prove it to me. You could check it out in Desmos, or if you're getting the hang of this, you can give me a rough sketch and show me one. So what we're going to do here is plug in our values so that we can create a table. And what I want you to pay extra close attention to is the fact that we have a 2 as our numerator instead of a 1 now. I would encourage you to go into Desmos and play with this and see what happens as that numerator value gets larger, but we'll look at this example together. So if I plug in -5, -5 plus 3 is -2, 2 divided by -2 is -1. Hello, oops, I'm in my eraser, there we go, -1. All right, if I plug in -4, -4 plus 3 is -1, 2 divided by -1 is -2. Whew. Okay, -2 plus 3 is 1. 2 divided by 1 is 2. -1 plus 3 is 2. Divided by 2 is 1. Whoop. And 0 would be 2/3. 2 divided by 3, right? Okay, so let's graph this and see if we can tell a difference between this and the other examples we've had. First of all, I do want to identify my asymptotes. X cannot equal -3. That's why I skipped it in my table. X cannot equal -3 because it's undefined at that location. So we're going to put in our asymptote at X equals, oops, wrong one. That would be +3. We want an asymptote at X equals -3. X equals -3 is our asymptote here. And then again, because this is a fraction without any additional values outside, unlike this example here, right? So this has a fraction and a constant that we're adding to it. That'll change things. But because we just have a fraction and no constants added, we know that Y cannot equal 0. So we also have a horizontal asymptote at Y equals 0 because you can't touch that. It is undefined there. All right, let's plot these points and see what we get. So at -5, I go up to 1, -1, sorry, down to -1. And then at -4, I'm down to -2. Okay. And then at -2, I'm going up to +2. And -1 is 1. And 0 is 2/3. All right, so it's a little bit hard to tell when we're hand graphing and just comparing when it's only 2, but hopefully what you're getting a sense for here is that this is pushing away from the intersection of our two asymptotes. So where your asymptotes intersect, that's kind of the center of this graph. We call it a locator point. It's kind of the central location of this graph where those asymptotes intersect. So when that numerator is a larger number, the curves push out further from that intersection point. So again, play with that with Desmos, see what happens, check it out, see if you can figure this out for yourself. All right, you should pause this now. You should try this one yourself, see if you know what you're doing. All right, what do I know? I know that X cannot equal 4. That's going to be an asymptote. And Y cannot equal 0. That's going to be an asymptote. So at X equals 4, I'm going to go ahead and put my asymptote. Ooh, this is being so laggy. X equals 4, we have an asymptote. Y equals 0, we have an asymptote. And these are going to follow that same exact pattern. So without even creating a table, because I have a numerator of 1 here. Sorry, my iPad is frozen. Let's try again. Come on. Okay, so our curves are going to look something like that. That's actually not quite close enough. It should be a little bit closer because we have a 1, and that's actually like a little bit too hard of a curve. You could plot these points and do a better job graphing it. It should look more similar to these first two over here and here because they both have a numerator of 1. And then just the asymptote has shifted, the vertical asymptote, which is going to shift our whole graph left or right. All right, let's do some more. Okay, now in this example, my horizontal asymptote is going to shift because of that. I got to move that 2 over with the Y. So the value of 2, when I subtract 2 to the other side, the value of Y that would make that 0 is going to be +2. So when I subtract 2 to the other side, so again, remember, we're thinking of this as equaling Y, right? So I'm going to subtract 2. I'm going to get Y minus 2 equals 1 over X. When I switch those, I get 1 over Y minus 2 equals X. So my horizontal asymptote is going to shift up to positive 2. My vertical asymptote is going to be 0 because that's the value of x that would make it undefined. All right, so let's see what we can do with this. If this thing would stop freezing, that'd be great. Okay, so at x equals 0, we have our vertical asymptote here. At y equals 2, we have our horizontal asymptote is shifted up because of that plus 2. And then if you create a table, which I would of course encourage you to do, you will see that your function looks like that. Again, spend time playing with these in Desmos, get a feel for how this works. All right, now what happens if we have a negative constant? So this whole function is now been multiplied by a negative. Remember what that does with like a quadratic when our arms are up, now our arms are down. So this has a big impact on our functions. So let's see what happens with a rational function. So let's create our XY chart and just kind of play with this a little bit. So I know x equals -1 is where I'm going to break the function. So I'm going to start at -3, -2. I'm going to skip -1 because it's going to be undefined. And then 0, 1 should give me an idea of what's happening here. Okay, so when I plug in -3, -3 plus 1 is -2. Negative divided by negative is positive, so this becomes positive 1/2. All right, when I plug in -2, -2 plus 1 is -1. -1 divided by -1 is a positive 1. 0 gives me -1 because negative divided by a positive is a negative. And -1 divided by 2 is -1/2. All right, so we have our asymptotes at x equals -1 is our vertical asymptote. Our horizontal asymptote has not shifted. It's just y equals 0. And now I need to plot these points here. So when I go to plot this point, -3, I'm going up only 1/2. When I go -2, I'm going up 1. And I would assume this curve will continue because that's how rational functions work. And then when I go to 0, I go down 1. And then when I go to 1, I'm down 1/2. So this curve looks like this. Look what happened. So look at the difference between these two here, aside from the shift, the vertical shift, of course, and the vertical asymptote shift and the horizontal asymptote shift. But despite that, what else has changed? The curves are on opposite quadrants. So notice in all of the functions we've talked about with positive leading coefficients, we have our bottom left curve and our top right curve. But if we make one of those negative, they're going to switch. We'll have a top right curve and a top left curve and a bottom right curve. So those are going to switch spots. Again, play with this in Desmos. See if you can get a feel for what's happening here. All right, you're going to try this one with a bigger coefficient and see what this graph is going to look like, and graph that for me. So where are my asymptotes? Ooh, this thing is so laggy right now. Okay, we're going to have an asymptote at x equals 0. We are going to have an asymptote at y equals 0. And then this factor of 5 is going to, again, push those curves out from the center, that locator point where the asymptotes intersect. All right, so if I plug in 1 for x, then I get 5. If I plug in 2 for x, I get 5 over 2, which is not 3. Come on. Ooh, ooh. 2.5. Get it together. Oh, 5. 2.5. Right? Woo. And then if I were to plug in values to the left, like -1, then I'd get -5, and -2 would give me -2.5. All right, so again, these are going to push out further. So over 1 up 5, and then over 2 up 2.5. So remember, we were really, really close to that center point when we had just 1 there, but this gets pushed way further out because we've multiplied by 5. -1, -5, -2, -2.5. Again, we're pushing this curve out away from that center locator point. All right, last but not least, this U-try combines all of the many things we have talked about, the different ways this function gets transformed. We have a negative coefficient, this -1 value in our numerator. We have a vertical shift because we have a value being added to that x, and we have a horizontal shift because we're subtracting something from the entire function. All right, so let's think about what all of that means. All right, I know that x cannot equal -2 because that will break my function. So that's my asymptote for that. I know based on these patterns, when I add 3 to the other side, -3 is actually going to be the value that breaks y. So I'm going to have a horizontal asymptote at y equals -3. And then that -1 I know is going to flip where so I'm going to have a top left and a bottom right as opposed to a top right and bottom left. So, but of course, I would create a table at least for a couple of values. So I would plug in -1, for example, to see where that point's going to be. So when I do -1, I get -1 divided by 1, which is -1, minus 3 is -4. So -1 gives me -4 down here. Oh, let me switch back to an actual. Come on. Here we go. Try again. Okay, so let's put that point right there. Come on. All right, so again, this curve is going to look like that. All right, then of course you want to add another point on the right-hand side. So at -3, -3 plus 2 is -1. -1 divided by -1 is +1. Minus 3, then we shift down 3, right? So -1, hold on, what do I do here? -1, what did we say we're plugging in? -3 gives me +1 minus 3 is -2. So -2 is my point over here. So this curve is going to look like that. Hopefully, the most important thing that you should be taking away from this section is being able to determine where your asymptotes are and paying attention to what that negative numerator does to your function and just getting a feel for the pattern of these. All right, now we are going to describe fully one of these functions. So this should be bringing you back to last week when we were describing functions, and now we're going to do this for a rational function. You're going to fill out this table because we're going to graph these by hand. And so again, I always want to start, and I don't know if I said this explicitly, but you always want to pick values to the left of the vertical asymptote and values to the right of the vertical asymptote so you can see both curves, right? So we want to look to the left of +4 and the right of +4 so that we can see the whole picture. So to the left of +4 would be like 2, 3, we're not going to have 4, right? And then we could do 5, 6, and then I'm leaving the rest of my table just to fill in wherever I feel like I need more to know what this curve looks like. Okay, so when I plug in 2 minus 4 is -2, I get -1/2. When I plug in 3 minus 4 is -1, I get -1. When I plug in 5, I get +1. When I plug in 6, I get +1/2. Okay, where are the asymptotes? We know we're going to have an asymptote at x equals 4 because that's going to be my vertical asymptote, right? The value that breaks the function for x. And then if we were to resolve for move that x to the other side and see what value of y ends up in the denominator, it's going to be y equals 0 is going to be my horizontal asymptote there. So let's go ahead and draw those in. We don't even have a coordinate plane here, so let's do that. Oops. There's our coordinate plane. We want to have a vertical asymptote at x equals 4. Boop, boop. That should ideally be dotted, but this thing is being so slow, I don't know what's happening with it. And then again, a dashed or dotted line there for that other asymptote. All right, so we go to +2 and we're down. So we know that this curve is going to be on the left-hand side over here. So at +2, we go down 1/2, positive 2 down 1/2, like right on my asymptote line because I didn't draw it perfectly. And then at positive 3, we go down 1, and this curve is going to look like this. Okay, then we go to 5 and we go up 1. We go 6, we're only at 1/2. So again, that curve is going to look like that. So now we've graphed it. Let's describe it. This is a rational function. So you name it by, the shape is the name of the function, assuming you know the name of the function, which we do in this case. Increasing, decreasing. Okay, so remember, we're looking for intervals where as we move left to right, as we look across the graph left to right, we're looking for values where y is either rising, increasing, the y values are getting bigger, or we're looking for when the y values are decreasing, getting smaller. So as I look from left to right across this graph, so if you kind of trace what's happening as we move left to right, the y values are decreasing. So on that first curve, when I hit that first curve, as I move over, the y values just get smaller and smaller and smaller. They're never getting bigger. Now go to the other side. We're starting really high up for our y values, but as we move to the left, my y values are decreasing. So this is decreasing from negative infinity to positive infinity. In other words, the entire domain. The entire function is decreasing the entire time. Okay, what is the domain? Remember, for these rational functions, we're going to say it's everything because it is, except the asymptote because can't touch that, right? So all real numbers except x cannot equal, in this case, positive 4. What about the range? Same thing, except now we're going to say everything except our horizontal asymptote. So now we're all real numbers except y cannot equal 0. End behavior. Okay, remember we're looking at the arrows. We are looking at the arrows. So we're looking at the arrow furthest to the left and the arrow furthest to the right, and we're asking ourselves, where are those heading? So on the left, and the other way we say this is on the left, we say as x goes to negative infinity, what are my y values doing? Y goes to negative infinity. See how that arrow is moving to the left? So it's going to forever to the left. Oh, no, not y, not negative infinity. Oh, get it together for now. Woo! Big mistake. Left is negative infinity for x only, not for y, right? What's my y value doing? So look at this arrow here. What, oh, oops, let's bring that back. Look at that arrow there, right? What are the y values doing? Well, they're rising. They're actually going up. So as I move to the left, my y values are getting closer to that asymptote. So what's y doing? Y is approaching 0. It can't get there. Remember, that's an asymptote, but that arrow says approaching, so it's fine to say that it's approaching 0. So as x goes to negative infinity, y approaches that asymptote. It's trying to get closer and closer to that 0. It won't ever get there. All right, how about on the right? So as x goes to positive infinity, or on the right of this function, what's happening to my y values? Well, now my y values, also we would say these are rising to 0. And in this case, my y values are falling to 0. Okay, oops, not that. Okay, so we rise to that asymptote on the left-hand side, and on the right-hand side, we're falling to that asymptote based on the trend of the graph at the arrows here. We already discussed this, but this is going to be discrete because of those asymptotes. 2 asymptotes definitely break this in a way that we need to pick up our pen to draw it. Is it a function? Yes. For every input, there is one and only one output. All right, your turn. Give this one a shot. Create your table, create your graph, and then check it and make sure you know what you're doing. So this video is getting really long, so I filled it out for you, but I am going to walk you through it. So again, always pick values to the left of the asymptote, the vertical asymptote, and to the right of the vertical asymptote. In this case, the asymptote is at 0. That's the value of x that would break this function. So I started with -2, -1, and then I skipped 0, of course, went to 1, 2, and 3. And that's how I got my my values. Again, just plugging in those values of x, solving for y, or f of x, as the case may be. This is a rational function. That's how we name the shape. We have an asymptote at x equals 0. That's the value of x that would break the function. I'm just going to remind you really quickly why our horizontal asymptote is at y equals 3. So remember, if we had the equation 1 over x plus 3 equals y, and we wanted to resolve for what, put y in the denominator, we would have 1 over x equals y minus 3. Multiply by x on both sides, divide by y minus 3, we end up with 1 over y minus 3 equals x. So what value of y would break this function? Positive 3. Hopefully you're starting to see a pattern here. This value is always where our asymptote ends up being. All right, end behavior. So we're going to look at our arrow over here on the very left-hand side, or as x is traveling to negative infinity. What are my y values doing? They're rising up to the asymptote at 3. They're rising to 3. They won't ever get there, but that's where they're heading, right? On the right, this arrow over here, what are those y values doing? They're falling. They're also falling to the asymptote though. They're falling to that 3 value there. They can't touch it, but that's where they're headed. Again, and that's as x is heading to positive infinity, or on the right. This function is discrete because we'd have to pick up our pencil to trace this entire thing. I feel like I completely skipped over a bunch of stuff. Okay, so decreasing. So as we read this function from left to right, so decreasing or increasing intervals, as we read this function left to right, I'm going to highlight it in green as I'm doing it. As I'm reading from left to right, my y values are getting smaller. They're decreasing. Check the other side. What is this side doing? They're also decreasing. So as I read the function left to right, I'm decreasing the entire way. So this function is decreasing over the entire domain, or we're saying from negative infinity to positive infinity the entire time, this function is decreasing. The domain is going to be absolutely everything except that vertical asymptote. So x is not allowed to be 0. Now I want to highlight a difference between this not equal to and the equal to here. So if you look right here, we have equal to, and right here we have not equal to. Remember that an asymptote is actually, that's the equation of that line. So the equation of the asymptote is actually x equals 0, whereas x is not allowed to be 0 is telling you that the function is undefined there. So the equation of the asymptote is what the asymptote equation is, but the function is broken where x equals 0, so x is not allowed to be 0 in the domain. So hopefully that clarifies those two things. Students mix those up a lot. We talked about end behavior, we talked about discrete, and yes, of course, this is a function because every input has one and only one output. Hope you are doing okay with this and that you survived this long video. Have a great week.